All right, welcome back. Hello again for another online lecture. Today we're going to be talking about evaluation measures for clustering. So hopefully you've already done clustering at this point in the lectures or read about it, or it's coming soon. You're studying this early, good for you. The tasks of classification and clustering are fundamentally different, so even though we're still taking in data, learning a function essentially does mapping from inputs to outputs. In classification, the output is a label. And in clustering, the output could be a label, it could be collections, it could be different things. But the main difference is that when we're training a clustering method, we don't know the right answer. So we don't have an example of the correct clusters given to us, whereas in classification, we assume that we do have the correct labels and classes given. So we'll actually talk a little bit about the difference between class and cluster in this lecture, and also then if you're doing clustering, how do you evaluate it? Because if you don't know what the right answer is, it's a little tricky to know how well you're doing. Same reason it's hard to do the training, it's also hard to do the evaluation. So for clustering, there are two main categories of evaluation measures, internal and external. Right? So internal methods are ones where it's based on the data itself. So we're looking at the structure of the data, the spatial orientation of it, inherent properties about the data and their relationships that help us evaluate whether this clustering is good or not. For external methods, we do have some ability to be given the correct answer, so we can evaluate, essentially assume that you do have a label of a certain number of clusters that you could use, but you don't have enough of them to use for training, or they can't be used for training for some reason, but you can use them for testing. So you can use them to validate that you're correct, but you can't actually rely on them during the test phase. So those are kind of two main groups of how we can do these. So look at the external first, because that's a bit more familiar. Assuming we have the class labels, so we know the right answer, and we weren't able to use it during training, but now we could use it during testing, right? So some of the same things that we've used for classification, you could still use. You can basically look at the accuracy of your clustering assignment. So the F measure also will give a good balance for that. But there are also a number of clustering specific measures that are useful because they take into account the kinds of things that we want clustering to be good at. So assuming that we know the classes, we use the original correct classes for all the data points. So again, we've got some number of points, right? And there is a correct kind of assignment for all the points that has been given to us. Let's say that these classes, these areas determine which one's correct. And we assign each one, I guess we better just use our notation that we have here. We have correct classes for the points to belong to. So we need some notation to define these measures that we're going to define. We're going to define something called a characteristic function. And it's really, you could think of another thing that it gets called, especially in machine learning literature, is an indicator variable. That's an R there. So an indicator variable, same thing. It's some function that basically takes in your data or your inputs or something and returns ones or zeros, right? And so this can be used, it's very useful for counting. If you can assign to you can use this for features as well. You have some function that takes in features of your data and returns a binary thing, and then you can count how many of a certain pattern occurs, right? In this case, we want to count how often we're getting certain things correct. And we're going to get back to our old friend, the contingency table or the confusion matrix, which counts the number of correct classifications and incorrect classifications, and so on. So these functions, just in terms of this notation, are called the indicator u, so on the variable u, right? And before we were given u are our classes and v are the clusters, right? So these are the right, the class. We say this is the true one, right? And these are the clusters that we've assigned, the ones that we have determined. We want to know if these are correct, right? So we're trying to match these two together and see how many of our assigned clusters match the correct class. Also, note from our definition here, we have R classes and K clusters, right? And so all we're saying here is that this function is going to give you a 1. If you give it 2 points, I and j, 2 data points in your set, we say, well, for that data point xi and xj, if they're in the same class, right, if they're both in class R, we return a 1, and 0 if they're not in the same one. And basically, you do this for all values of R. And similarly for the clusters, you'd say the 2 data points are in the same cluster S out of the K clusters, then we give that a 1, right? And so if you sum up on any of these dimensions, it's basically why we're doing this, we want to be able to have a contingency table like this, where we say that if the points are actually in the same class, right, these are the true things, whether the data points are actually in the same class or not, right? So we've got in our data set here, we've got pictures of different things, and these are people, and these are pets, and these are cars, right? And you really want to be able to get them correct, at least in that each category, right? And so if they're in the same class, then it's in these rows, and then if we put them in the same cluster in our algorithm, then it goes by the columns, right? And we want to count how many times they're correct, right? So these are our gold standards, right? These are the ones where we picked the clusters for a pair of points, and we said these 2 points were in the same cluster. They're both people, and they're actually both people, right? And similarly, if they're in different ones, and we say they're in different ones, these are both good. If I don't know if people can see, I might not be able to see red. These would be bad because these are things where we got it wrong in some way, right? These are good, but you might care about certain things more than others, right? You might care about certain types of errors more than others. There's another lecture, maybe in your future or your past, depending on the online nature of where you are in the course, where we talk more about all of these components. But in case you've forgotten, these all have very meaningful and natural names. It's the true positives, right? True positives, the ones that you said were positive. They were both in the same cluster. It's just positive case being that you said if this binary thing, saying that they're in the same cluster, right? So when it comes out to 1, when our indicator function comes out to 1, that's a positive case. It doesn't mean it's correct. True means it's correct, right? So we have a true positive means we said they're together, and they are, right? And then we have false negatives, which would be the opposite, where we say we said they're different, but they're actually the same. So they're negative. It was a negative because we said they aren't, the 2 data points aren't in the same cluster, but in reality they are in the same cluster, so we're wrong, and that's why it's a false negative, right? And similarly, this is the false positives and true negatives, and so they all have a very particular set of things, and true is the thing you want because you got it right, but these 2 different types of errors, being false because they're saying they're in different classes when they're in the same one, or the reverse, saying that they should be in the same class when they're in different ones, are different types of errors, and it's important to be able to do them differently. These will come up again and again in different parts of the course, but we're just focusing on the classification nature of it right here. What we're going to do here in this case is add these cases and add these cases to give us certain statistics, and m is going to be the sum of all of them, right? So the total number of pairs of objects is going to be m, so you have, it really should be that the sum of all these should add up to the number of pairs, right? And so you can do that by saying it's n choose 2, which will give you that formula. So that's a good way to check if your calculations are correct, because your counts in your contingency table really should sum up to the total number of pairs. And once we have those numbers, the A, B, C, D, and we can have it up here just so you can see it again, right? You can even just do it this way. Cluster and class. Just as a reference, a very messy reference. These are three kind of popular and useful indices for evaluating whether you're doing well, right? So rand index, you combine the A and the D together and normalize it by the number of possible cases, right? So these are all the ones where you got right, so all the trues. It's kind of a probability of you being correct on some random case. So what percentage of them do you get correct, right? It's kind of like an accuracy for that. It may not be really the only thing you want to optimize, but you'd hope you're doing pretty well on that. Jacquard measure. Let's see, rand, there's other things about rand. So the next slide we've got more points on kind of why they're useful. The rand index focuses on relative accuracy. It's how many times you get the agreement correct, and it's normalized for the size of the data. And so it can definitely be used. If there's no labels, it's perfectly fine to use this. Jacquard metrics, you're just really looking at A, so A is really the perfect ones, the true positives, where you got it all correct. Not perfect, but they're the ones that are in this, assuming that it's important that you get the ones in the same class, so that's an important thing you're measuring. You're taking that and normalizing it by all the other things that you didn't get that involved 2 points being in the same class. And in a way, this gives you the similarity between two clusterings. And then this Folks and Mallows one is a bit more complicated. And if you're really wrong, if the clustering and the class are really far apart, then this can still give you a useful measure, because you can imagine some of these ones, if you're talking about the probability that you're getting any of them right, but if they're totally different and you almost have no agreements on which pairs are together, your rand index here is just going to be really low, and you can't really tell if one's better than another. Whereas this is normalized in a way that it would still be a useful information even if you're really far off. And it kind of has a measure for the bunchiness of the data, so how grouped it is together. And this one approaches, yeah, so as and this, it says this on the next slide already, but as U and V kind of diverge, like, so if they're more and more different, so if your clustering is not very good, then this one approaches 1, but in that case this one approaches 0. But again, they're normalizing the true positives by a combination of all the true positives with the way you got it wrong, right? So it's kind of looking at each of these axes and combining them together and then normalizing it. So these are some of the ones that kind of can be used. Like I said, the other standard measures that you can use for classification can also be used here. You have to modify them a little bit. So if you want to use F measure, then you need to have precision and recall that are relative to the class and the cluster. So we could talk about, how accurate we are at getting the points in a particular cluster rather than all the data together. Right, so here is where we're clarifying that whole thing about what class and cluster mean. And so let's just draw it explicitly. So we could say that the class that the data truly has, so when we get it given to us by Google or whoever, or some study or some database, it says these are the two classes, U1 and U2, and these are correct, right? And then we have a different assignment of these, right? We say that all these points are in cluster V1, and that all these points, I'll do a dotted line just in case people can't see the difference between the colors, are in V2, right? So the dotted orange lines are the clusters. Sorry, I will make it dotted. And the blue solid lines are the classes, right? And the class is truly in the data because these are pictures of people, of cars, of pets, and the clusters are the things that we've assigned them, right? We might be correct, we might not be. And we want to have alignment, so you could just count how many you are correct or not. And that's kind of what F measure does anyways, right? Because we're looking at ratios of correct versus normalized by each set. Right, so we need a modified version of precision and recall to do this, and so we have this MIJ, which is just going to be the number of objects in the true class J that we also have in our cluster I, right? So we'd say the precision is how many, if you think about that, number of objects in class J that are in cluster I, right? So there's 4 objects in class 1 here, and they're all in cluster 1, right? So here we'd have 4, right? Because that's all of them. And then Ni is the number of objects in cluster I, and in that case we've got 8, and so we're not doing very well. Our precision is only half, right? Because we've got them all right, but we're over guessing them. And then the recall is saying the number is that number 4, right? But divided by the number of objects actually in the class, which is also 4, right? So in this one, we're doing perfectly. We recalled everything. We got them all, but we overdid it, right? And so that matches the same kind of intuition we have with labeling, with classification, sorry, for precision recall. If you've done that topic yet, where recall is like, did you miss any of the positive cases? And precision is, did you label any positive cases, any negative cases as positive, right? So if you're doing disease diagnosis, which is kind of the clearest one where you want all these to be right, is, did you miss any people who have the disease? Is your recall, and that's very important. And precision is, did you incorrectly diagnose anyone with the disease who doesn't have it, right? And you might be able to get away with fixing that depending on the disease and the treatment. But if you miss a diagnosis, you're doing badly. So in some domains, recall is more important. In some domains, precision is more important. Generally, you want them both. F measure tries to combine them together. And so this formula for it is the same that you would have seen beyond clustering, but now it uses this class and cluster version of precision and recall, right? And so we have weighted combination of the precision and the recall normalized by the sum of them. And this gives you the F measure for that class. And because we now have a number of classes and clusters, we could say we have this pairwise F measure, right, that we've created. And then the full F measure, which is over the entire data set, is run over every class, right? So for every class, we iterate over it, and we were using J for class before too, right? So I'm gonna check. For every class, we pick the highest cluster so that we get the highest F measure, and use that one, and then we normalize it by, let me check what MJ is the number of, actually the number of objects in that class, normalized by the total number of data points, right? And so that's one way to do it. As with any of these things, you could try a different measure and see if it helps you tease out differences, but then you'd want to also justify it and see if it's named anywhere else. And if it isn't, you should name it yourself. But not every way of combining these is useful. This is kind of useful because you're weighting the strongest response of your clustering algorithm, and then weighting it by the size of each class. So you might be doing well on this class, but if the class is really small, it's not going to be that important. If it's a very large class that covers half the data, and you've got a good, your max F pairwise score on it is good, then you want that to contribute more to this F measure to say you've got pretty good performance. And finally, one other measure you might want to consider, and it's kind of a useful tool in almost all areas of data science and machine learning, is to look at an entropy approach, so a probabilistic approach to measuring whether you have a good clustering. And again, this is when you know what the correct classes are, but you couldn't use them for training. You could define a probability, ij, between, like we had before, between two pairs of points, ij, in the data, and then count how many you said were in a cluster and they're actually in the corresponding class, and do that as a probability over all the data, right? This ratio would give you a probability that you got it right, essentially. And then you can define entropy of these probabilities, right? So we have a probability distribution where there's multiple entries here for every single class. We'd have, so the entropy on cluster I, so your cluster, you define the entropy for all the classes, right? And that would have a bunch of probabilities. And then these would they add to 1? Because I think it's always good to make sure you think if your sum here sums over something that adds to 1, right? So you're summing over all of a particular cluster I. So this is your cluster that says all these images are people, and you're going over all the data points for all the different actual classes and seeing what's your probability your model says that some data point j is in that any data point j that's in that class is also, that you say is in your cluster I. Right, so your probability here is using the sum of all the numbers you've got, and assuming that this probably now gives you your ratio. And so for every one of these, you would have a probability, even if it being a different class and you getting it basically wrong. And so that should sum to 1. The p's should sum to 1 over this. And and then you have the entropy. All right, and so entropy, as we talked about hopefully before, or we will in the future, gives you a measure of probability, of uncertainty. Right, so probability tells you how likely a particular outcome is. Entropy tells you how much uncertainty is there about all of the outcomes in this distribution, right? You're summing over a bunch of events and saying how much uncertainty is left over, right? If all of these probabilities basically are one, or just a single 1 and the rest are zeros, then there's no uncertainty. You know exactly what the right answer is in all cases, right? If that's not the case, then there's kind of uncertainty left in every one of these assignments, and entropy measures that together and adds them. So it's a useful approach, and it helps you tell how much uncertainty you have left, how far you are from the total knowledge of getting everything correct, right? And if your entropy is high, that means you're not doing very well. And if your entropy is low, you've basically got complete certainty. And in this case, since we're counting how many you got correct, the probability of getting it correct, getting an entropy of 0 would mean you're perfect, right? Which would be unlikely, right? So if your model comes out perfect, you should question it and see if you've just copied the wrong data set over, like any good programming situation. So then for your entire clustering, remember this is just on one particular cluster. And so for the entire clustering, you just have to sum over all the clusters you have and normalize it. This E is, of course, from that formula. And then you weight it by how many points are actually in that cluster from your, so that's ambiguous, number of points I in cluster I, right? So this is a number of points that are in your cluster I, not the true class C. As a ratio of all of the data points, so you're weighting it. So this can also be a useful measure. Now on to internal measures for evaluating cluster performance. If we don't have a correct labeling, so we don't know, like in my case of there's a bunch of images of people and pets and what did I say? Cars. But no one tells us the right answer. You say, oh, we cluster these into 3 groups. We maybe even tell you there's 3 clusters. And how do you know you're doing well? So these are basically protocols or hopes for what a good clustering would be like, right? So 2 main kind of concepts are that you want the clusters to be compact and you want the clusters to be well separated. Right? These are sensible things we claim to want your clustering to have. And some of the algorithms that we talk about for clustering, if you've been to those lectures yet already, explicitly kind of target some of these things, right? To say, well, I want to make sure that if data points are close together, that they're in the same cluster, right? And if they're far apart, then I want, if there's a gap, then I want to use that as the separation point to say that they should be in a different cluster. But it could be that data points that are close together happen to be in the same cluster because you can't see all the information, or it's kind of an arbitrary line that people have decided and it doesn't really make any sense, but that's the labels that we have dealt with, right? So if you're doing vehicles, it could be, car and SUV, right? And wagon or some other thing, or crossover. There's all these things that are like, I guess we could say something more specific, like a sedan. There's types of cars, right? And they're really all cars. And sometimes when you get over here, you're sure it is actually quite different than the car with the four doors and not very high off the ground than an SUV. But along the way, there's basically every combination and gentle change from this normal car to what we would call an SUV or an off-road vehicle, right? But for humans, it's very clear that this is a wagon, and a wagon is different than a sedan because it is longer and the proportions are but it's not clear numerically, right? So it's very possible and common that the true classes of a data set aren't necessarily that justifiable when you're looking at distances and density, right? So it's a tricky thing. That's why clustering is harder than classification. But we can say that the cohesion, right? So I'll try and color them a little bit here again. We're going to say red dotted lines are cohesion. What we're trying to do is to say that that all the data points are close together, right? Whereas this set, if this were one set over the whole thing, that would have less cohesion, right? So this is better on cohesion, the small one. And then, what other color do I have? I have green, which is not a good color. Separation, obviously, is this, it's the distance between the clusters, right? And so we'd say that separation is how far apart are they? Are they far or are they close, right? And if these ones are separate, having them be very close together, we would say this is a very bad clustering because they shouldn't be so close. You should just merge them, right? But maybe the humans decided that this is really an important class. So it may not work, but it seems like a sensible thing to have, these two concepts. So using those as our internal measures, given that we don't have the right answer, we can define a bunch of numerical computations based on that. So we have proximity of 2 points, and it could be any similarity function. So we have distance metrics that we've talked about in class in other sections. So it could be Euclidean distance, it could be Mahalanobis distance, Manhattan distance, it could be some kind of probabilistic thing. Any way to figure out that they're close together, right? So you want this number, the proximity, to be high. You want them to be, you want to have a high number if they're very close, right? And the cohesion is the sum of those, and so your cohesion is high if all the points in a class are close, right? And then you'd sum that over for all the classes, which is quite simple. Overall cohesion, we're just talking about looking at all the different clusters and summing it. For that, weighting it for the size of each cluster. So the same way we did that for the entropy, you could weight the importance of a cluster by how big it is, and say you want the large clusters to have lots of cohesion and be tight, and if some small cluster is a bit more spread out, it doesn't matter as much because maybe it's an error anyways. So that could be done in various different ways. All right, so another type of proximity method could be cosine similarity, and we talked about that before, right? If you have two data points, you're talking about the angles to the vectors of those data points rather than the distance between them as a Euclidean thing in that dimension. That can be quite useful. So this proximity measure could be anything that gives you an idea of distance between them. Then in terms of this separation component, I apologize for these slides. They were not updated. I will update them for the posted slides that you guys get, but I'm just going to go through with the lecture. Separation, we're talking about whether these data points that are in a cluster are well separated from another cluster, right? You want to be able to say there's a distinct line between them. And like I said, it may not be always be possible, but that's what we're aiming for, right? So this separation is what we're looking for. And so you could just measure that as distance, but if you think about it, what is the distance between two clusters of points, right? Is it the distance between the mean, like the kind of average center of the data set, or is it the distance between individual points, right? So what we call a single link takes the nearest 2 points between data sets and say that's the distance between the clusters, right? And complete link takes the furthest 2 data points and says that is the distance between the two clusters, right? Neither of these is a very good measure, but they're clear and they're consistent. And if you're judging yourself on all your clusterings, at least it'll give you a consistent thing. And maybe you care about that. Maybe you don't want individual points to be too close because they're all, they should be quite separated. Or maybe you just care about the outliers being too far away so that, you know, it's okay if some classes are near each other in individual points, but if their most different elements are basically unrecognizable, then you shouldn't be in the same class, right? So when you have cars and SUVs and wagons and motorcycles and all these things in there, you say, well, the motorcycle is too far. Even a sedan is too far from an SUV. They're very different. So somewhere in there should be a difference of a line, right? Whereas if you used single link and said, oh, is the distance between the closest ones too close, you might never get a good one because there's always a very close match and you have to draw the line somewhere. So they have pros and cons. It depends on the data, and you really can see the difference if you try them out. You'll get a different clustering. If you're optimizing for one of these measures, you get a different approach.